Okay, so this time we're going to look at the parts of a wave, or maybe the anatomy of a wave. So the first type of wave that we're going to be looking at is a transverse wave. I can tell that this is a transverse wave because it looks like the wave is going up and down. Okay, so transverse waves look like this. They go up and they go down. The crest of a transverse wave is the highest point. The trough is the lowest. The word trough can also refer to, like in agriculture, to the like watering things that kind of look like this for cows. So like a cow would come up to this and like drink out of it. This is a blue cow, I guess. That's a cow. But yeah. So the trough is like the bottom, right down here. Trough. Crest is the highest point. Like when you crest a hill, you are going over the top of that hill. And wavelength is the distance from crest to crest or from trough to trough. Realistically, if you were to just like turn the page upside down, the trough would become the crest and the crest would become the trough. It doesn't really matter. It's just a matter of perspective. You can call either one the crest or the trough. No big deal. This symbol here, lambda, that is just the symbol that we use instead of writing out the word wavelength. So for example here, I could get rid of the word wavelength down here, and I could instead just draw a lambda. Lambda means wavelength. Okay. And then amplitude is the distance that particles are displaced. So we'll talk about amplitude in a little bit more details here in a second. So we're just going to move on to talking about compression waves. So again, these are all the characteristics of a transverse wave. Crest is the highest point. Just a little background also. Like remember up here where I talked about wave fronts? These are the crests. Okay, those are the crest. Those are the areas with the most energy because it displaces the matter the furthest. So if you think about like if this little green dot here is a water molecule, it goes from here down to this point down here where the trough is. That is being displaced. It goes from this center red line down to the bottom. So the crests and the troughs are wave fronts, and they are the areas with the most energy. Okay, so we have a very similar situation in the compression waves or longitudinal waves. Longitudinal or compression. Okay, so these are longitudinal or compression waves. They have basically the same parts, but they look different, so we give them different names. Instead of a very high point, instead of a high point and a low point, we have a squeeze point and a pull point. Okay, so where transverse waves go up and down, longitudinal and compression waves, they go squish, pull. Squish, pull. Okay, the squish zones, the compression zone here, like this place right here and this place right here, those are called compression zones. Those are equivalent to a crest. Okay, you can think about them as crests. They're the places with the most energy. The rarefaction, this area and this area, you can think about these as the trough. They still have the same amount of energy, because if you think about like a spring, if you pull a spring apart, it's going to want to snap back down to its smaller size, right? So it still has the same amount of energy. It's just an energy in the opposite direction. Whereas this one is squished, and so it wants to expand. This one is pulled apart, so it wants to squish back together. Okay. So the compression zone, the peak compression zone here and here, has the exact same amount of energy as the rarefaction zone here and here. They're just in opposite directions. One is squished and one is pulled. They still have a wavelength, but instead of going from crest to crest, you go from compression to compression. So it's just, it looks different, it has different names, but it's really the same thing. Yeah, so that's basically that. Now let's talk about amplitude. Trying to visualize amplitude in a compression wave is pretty difficult. It has to do with how compressed something is, but we're not really going to talk about that. So, because it's just kind of hard to wrap your head around, and it's just not that important. So what amplitude really is the intensity of the wave. And we're going to look at amplitudes on transverse waves because it's a little bit easier to picture. If we look at these two waves, we'll call this wave A and wave B. They are the same wave. Here's a crest. This is a crest. This is a crest. And here's another crest right here. Okay, and we can see that they line up. So if you remember, our wavelength, or lambda, is equal to the distance from one crest to another. And we have an equal wavelength on both of these, waves. Therefore, these are the same waves. Just think back to this. The only thing that makes a gamma ray different from a TV ray or from a radio wave is that the wavelength of a gamma ray is much, much smaller than a radio wave. The frequency, or the wavelength, is what makes them different. So because the wavelength is the same here, these are the same waves, even though they look kind of different. Well, what is different about them? It is their amplitude. Okay, amplitude is the intensity of the wave. So basically, it's kind of like saying how much energy it has, or how intense you will experience it. Okay, so if we take the center line, so we can see that the amplitude here is definitely much larger than the amplitude here. See, this arrow is longer. So you can think about amplitude like an amplifier for like a guitar or any other instrument. What an amplifier does is it takes the sound from your guitar. It makes it louder. It adds energy to it. Okay? It doesn't change the notes that you're playing. It just makes them more intense. It makes them louder. That's what an amplitude, or that is what amplitude is all about. Amplitude is the intensity. It doesn't change. Having a different amplitude doesn't change the wave. It just changes how intense it is. So more amplitude on sound gives you louder sounds. Less amplitude is quieter. If you were talking about light, more amplitude is brighter, whereas less amplitude is dimmer. Okay? So just depending on what type of wave it is, the amplitude can change, and that gives you different properties. All right, and last characteristic, we need to talk about frequency and period. They are interesting. A period is how many seconds it takes for a wave to complete one wavelength. Okay, so if we have this wave, it's traveling this direction, and we are trying to measure how long it takes for one wavelength to happen. So we're measuring how long does it take. Let me move this so we can see a little bit better. How long would it take crest B to get to the point where crest A is at? Okay, that would be the period. How long, how much time does it take for this point B to get over to where A is? That would be period. Frequency. So remember, and waves usually move very, very fast. So you would probably get a very, very tiny number that looks like this. Not a very helpful number. Very tiny, very annoying, right? So using period isn't always the best thing to do. So what they came up with was they're going to measure what scientists came up with instead of trying to measure these very tiny amounts of time. It's actually easier to figure out how many times a wave cycles in a second, and that is what we call frequency. So frequency is essentially just the inverse of period. Well, it is the inverse of period. So instead of saying how long does it take for point B to get to where point A is, it's saying how many times how many crests can we count that go by within a second? Okay, and you'll often see questions that will ask you to convert from period to frequency. If we are looking at this equation, frequency is equal to 1 divided by time. It's actually super simple. So let me give you a couple examples. First example, we have a period of 1 second or half a second per wave. The frequency would be 2 waves per second. So how we got that, F is equal to 2, and we need to figure out the period. Okay. If we plug it into our equation, frequency is equal to 1 over period. Plug in our numbers. 2 is equal to 1 over t. Solve for t. There you go. The shortcut is just to flip the number. Okay. So essentially, if I said that let's say that I told you the period of some wave was 0.05 seconds, and I ask you what the frequency is, all you have to do is just give me the inverse of this number. Just flip it upside down. 1 over 0.05. And then put Hz, because Hertz, oh, I should put that here actually as well. Hertz is frequency, period is seconds. Okay, so we can do that again. Let's do it the other way. If I give you a frequency of 647,522 Hertz, what is the period for that wave? Well, just flip it upside down. 1 over 647,522 seconds. There we go. It's that simple.